Okay, so what we were discussing about the WebHDFS REST API. So we would be talking about WebHDFS REST API first of all, and you would go through a demo on WebHDFS REST API. Basically, we'd be covering standard HTTP operations like get, put, post, delete, and file-based operations on HDFS like open, get file status, list status using protocol like HTTP GET and others, some of the commands like create, mkdirs, rename, then set permissions, etc., which are based on HTTP put. So that could be the first demo on WebHDFS. Next, we would be jumping today on MapReduce. That first we will be covering on MapReduce some of the basic introduction to MapReduce. But before that, I would walk you through a guide of some of the sample Java programs, core Java programs basically, on like collections, generics, multi-threading programs, like some of the sample core Java programs which is required before going through the programming into Hadoop MapReduce. So these programs have been needed, and also I'd be sharing with you a complete step-by-step guide on each and every program sample. So before that, just should let you go through that how to write programs on Java in Linux environment, specifically on Hadoop cluster. So we'll be walking through on today on the installation of Eclipse on Linux desktop so that you guys can start coding on Java and MapReduce. This is one of the important and essential part of MapReduce. So we would be also having some little bit of theoretical side today, just being highlighting on MapReduce, because MapReduce is pretty vast one, and it is one of the core part of Hadoop programming. So next we'd be starting about MapReduce programming. So one programming we'll be working on today, if time persists, that's word count. So we'll be writing right now code, not any more jar files. We would write our own custom code using Hadoop MapReduce. So that's pretty much about the agenda for today. So let's get started. So before starting WebHDFS, let me start the Hadoop services. So as you can see, I have just booted my Hadoop server. That's my Hadoop cluster, which is a single node Hadoop cluster. Now here, I have a local name node data node directory. So just make sure that whenever you are starting your Hadoop services after booting up the server, so just normally if you just go ahead and format the name node and starting the Hadoop services, most of the times there have been issues coming up, like your name node would not be starting up, or data node is not being starting up, or both of the name node and data node, both services would not be starting up properly, though you have formatted HDFS name node and you have started properly. It is due to the fact that there is always some log files that's being present. That's one of the files that you can see that I have just going to delete right now. That's called version file, which is residing inside the data node and inside the current directory. So this version file actually consists of basically the FS image, edit log information, and each and every time whenever the data node service is going to start, the job details, job IDs, also the file directories, file IDs, metadata, it's being consist of. So next time whenever you are going to go ahead and after booting up the server, once again you are just trying to format the name node and starting of the services, due to the existence of the previous version file, the new services may not booting up properly, so it doesn't, so sometimes it creates issues due to the existence of the previous logs and previous information. So what we need to do in that case, we need to delete in that time the version file. Just do a simple rm, sorry, and then go ahead and format the name node. Then start the services. So this is one of the troubleshooting trick. Whenever in Hadoop cluster we have been facing regular issues like name node is not booting up, data node is not booting up, or sometimes both of the services are not booting up. So this is one of the resolution steps whenever we face such types of issues in real time. Right. Right, all of my services are running Hadoop services. So before starting WebHDFS, some of the points are there about WebHDFS. So Hadoop provides basically a native Java API
Hello.
to support. Yeah.
What is that JPS? What is it starting?
JPS is full form is Java Platform System, which comes
Oh,
after with JDK basically. So if you install JDK, then only JPS will be present in your system. JPS is a service, and using JPS in Linux, we check that how many services or processes is running right now. It's same like in Windows. Your process explorer, or what you call as task explorer, same like that in Linux.
okay. Why you did formatting then?
I formatted the HDFS name node. If I didn't format, so it would just consist of the state of the old FS image, edit logs, the earlier informations, file metadatas and all. So in that cases, my
So each
services would not
time,
be disturbed. Yeah.
we have to do that.
Each time means if you suppose booted up your server, suppose you have shut down and next time you are restarting. So it's recommended that you format the name node and then you just starting your services, Hadoop services.
Okay, okay, fine.
Okay.
Thank you.
Alright, so what I was talking about WebHDFS. So Hadoop provides a native Java API to support basically the file systems operations such as create, rename or delete the files and directories, open, read or write the files, setting permissions, etc. Now there is some of the great applications are there for running within Hadoop cluster, but some of the use cases like where an external application they need to manipulate the HDFS, like it needs to create the directories and write the files to the directory or read the content of the file which is stored in HDFS. So for that purpose, Hotworks they have developed actually an additional API to support the REST API based requirements based on standard REST functionalities. So what is this WebHDFS REST API? So WebHDFS concept, it's actually based on standard HTTP operations like get, put, post, delete, of course, and there are some operations like open, get file status, list status, these are all using the HTTP GET. Other types of operations like creating directory, like create, mkdir, rename, set permissions, these are all relying on HTTP put. Now there are some append operations like file appending operations which is based on the HTTP post, whereas delete operations on files which is based on the HTTP protocol, that's HTTP delete. Now basically when we are working on HDFS REST API, that's Web HDFS, we need to also have a strong security because we are all working through HTTP protocol. So here that time authentication occurs, it can be based on user.name query parameter as a part of HTTP query string, or if security is turned on, then it relies on Kerberos. So basically,
Hello.
yeah,
Is it like Java Web Services?
quite similar like Java Web Services. I mean, you can say like URL wise, it
Like
will be looks like
in Tomcat server, you'll hit the server, right? Is it like that?
not com server. It's actually like you know RMI, Java RMI, remote message invocation, remote method
Uh,
invocation, Java
yeah,
RMI,
yeah, yeah.
Corba. So
RMI.
yeah,
Yeah.
RMI and Corba. So it's a little bit like RMI. But here it's very simple. It's just like whatever the operations we used to do through HDFS commands, HDFS file system commands, like through HDFS shell, HDFS DFS command, same operations you could be able to do through HTTP protocols. So just like I want to create a file or a directory through HDFS, so FS shell command, what I will write, I would write simply HDFS DFS mkdir, then the directory name. But the same operations if I needed to do through the REST API, so I need to write a complete HTTP based URL. Through the URL format I need to do the operation. That's all.
Oh, okay. Yeah, thank you.
Okay, thanks. So how the standard URL looks like? So it looks like this for web HDFS. Like we need to mention the host, then the port number, then web HDFS version 1. Queries we need to pass operation ampersand user.name equals to username. So this is the standard URL format of WebHDFS. Now in some cases the name node also returns a URL using the HTTP 307 temporary redirect mechanisms with a location URL that's to be referring to the appropriate data node. So in that case the client needs to follow up that the URL to execute the file operations on that particular data node. So in order to configure WebHDFS, there is a little configuration is needed that you need to
Uh,
do.
Sorry to interrupt. Is the video getting recorded?
Yeah, I think so.
Okay.
So there is a little bit configuration is being there to enable web HDFS. So we need to make a change in HDFS site.xml. So to open HDFS site.xml, go to the properties and just add one additional property to enable web HDFS. Value should be the property. So here we have mentioned the node name as a dfs.webhdfs.enabled to enable the webhdfs property, and value should be true. So that much the property that we need to add, and can save and exit then. And you can just can come out. Also, to start working on HDFS, you need to install curl. So just install curl. Alright, let's start the command. So the first command that we would execute now is check directory status. So basically in the output of web HDFS, if the command is successful, it would always give us the output as HTTP 200 OK. and the respective content type, like what are the types of application. Mostly the content type is application JSON, and the content type expiry date and time, set cookies, values, etc. So let me execute the first command. It to have Carl, localhost, username, since the username of this cluster is trainer, so that's why I mentioned as user.name as trainer. When you would be working, you can mention as respected username of your system, and then mention in the operation command, in the operation parameter, just mention the ops that you are performing. So here through this command I would like to check the file status, so I have just mentioned get file status. So the command that I have executed here, it is very similar to Hadoop ls file system command. So that would be very similar if I needed to, if I write HDFS DFS ls. So through this command in HDFS shell, we would just check the list of the files that's being present within the HDFS. So similar command I have given for WebHDFS. So there is no file right now in my HDFS called /temp. So that's why it's been showing up that file doesn't exist. Now, similarly, if I give this command, so this is a similar command that I have executed here. So we can write either HDFS DFS, or either we can use Hadoop FS. So both are same. Hadoop FS we used to work in earlier versions of Hadoop, that's Hadoop 1.x. Hadoop 2.x onwards we can directly access through HDFS command. Next command that you can write for WebHDFS is to create a directory. So to create a directory through WebHDFS, the command you need to execute is car x. You need to use the HTTP protocol, that's put. So you can see that I have just created a directory. It's called WebHDFS. And next, if I need to check what is the name of the directory that I have created, list out the directory, so I'll be able to see that the directory has been created, that /temp. So that would be the similar command. If I just type HDFS DFS ls /temp. This is the HDFS shell equivalent command. So what the operation that I have did here through WebHDFS. Now this equivalent Hadoop file system command, if I need to execute, this should be the command. The next command that I can perform is how to create a file in WebHDFS through WebHDFS. So you can write car, again put http localhost WebHDFS v1 temp WebHDFS test.txt. Suppose that should be the file name. User.name, operation is create. So the file has been created. Now the similar operation also, if I needed to do, so what I could do, I just can create a file in HDFS. So I just could able to write like HDFS DFS mkdir. Then I could be able to write the directory path and the file name. So that should be the equivalent command for Hadoop FS shell. So basically, what are the meaning of this command? Few of this first parameter like carl, I, x, ht, like this. So basically, why we are using here carl? So carl is typically it's easy to use. It's a Linux carl that's which is being utilized to perform the standard operation through the HTTP commands. And with carl, there are some popular parameters are there with Linux carl, just like -l. -l, it just tells you like it actually tells carl to follow the redirects. Then -x, that means it indicates the standard HTTP method to use. -h, that tells up, it actually adds a header to the request. And -t, it actually points to an upload file. Okay. So similarly, in order to put suppose from a file from your local system into HDFS, you know that for HDFS file system shell commands, you need to use the commands like put or copy from local. But if the same operation, if you need to perform through web HDFS, so what you need to what command you can perform over there, that is should be carl t web HDFS test.txt http. Suppose make sure that you have web HDFS test.txt in your local drive. So this is the command that we need to use whenever we need to perform a copy operations of the file from the local system into HDFS through web HDFS commands. Now you can of course validate the command through the standard Hadoop FS shell command after performing these operations through fsls and then the file system names. So that could be your web HDFS command for this. But before performing this command, make sure that you have the corresponding file should be present in your local drive. So since I don't have right now this webhdfs.test.text right now in my local drive, so I'm not executing that this command. I am going ahead with the next command. So in the next command, what I am trying to do through HDFS is basically to open and read a file. So in that case, we can use card with -l option to follow the HTTP temporary redirect URL. So what I'm using card IL for redirection purpose, giving the URL -1 temp web HDFS, then web HDFS test.text, what I have created already inside HDFS. I am trying to open this with my user permission as this. So we need to mention actually the location, exact location where the file is going to be present. So what we can do next is basically we can specify the actual location as well. When set offset value. So the similar command, if we need to perform the similar operation through Hadoop file system command, so the command that we need to execute for this, so that could be bin HDFS DFS cat command, cat temp web HDFS, then web HDFS test dot text. So that should be the command by which we could be able to open and read a file. So the next command that we can perform through web HDFS is how to rename a directory. The command should be like this. Nora, you are not able to hear me. Okay, I have unmuted and muted me once again. Are you able to hear me right now, Nora? Nora, are you able to hear me right now? Hey everyone, am I audible right now?
Yeah, yes, to me you are audible.
Okay. Okay. Nora is not able to hear me. I hope Rakesh and Amir, both of you are able to hear me, right?
Yes, I can hear you. This is Amir.
Yes, I can also hear you.
Okay, great. Nora, could you please could you please check from your side if there is any issues with your speaker? Because Amir and Rakesh, both of them can hear me. Okay, and I think from my side, my mic is also working fine. So please check from your side if there is any issues. You can see the screen only. Okay. Yeah, yes, please. Please disconnect and join once again if that solves your problem. We are recording the session at all, so no issues. So what I'm doing here through this command, I'm just renaming the directory, the existing directory that I just created a few minutes back, that's temp/webhdfs. Now through this webhdfs command, I'm just trying to rename this existing directory. So I have just renamed it as webhdfs-new, and I have put it here, the operation name as rename, and I'll just mention the HTTP URL of my name node, and just took up the HTTP operation as put, and the redirecting operations as X and I for curl. Alright. So after that, the next command that would be, similarly, if I just go ahead and check the operation through normal Hadoop HDFS shell command, be like this. Okay, great. So the next command that I'm going to perform right now is to delete the directory. So this scenario results in an exception if the directory is not empty. Since a non-empty directory, it cannot be deleted. So make sure that when you are performing this command, the directory that you are going to delete is being empty. If the directory is not empty, so it would not be deleted, because a non-empty directory in Linux, it cannot be deleted. So what I'm doing right now to do this, so I'm using again the parameter as I and X, and the operation would be HTTP delete. Localhost WebHDFS temp operation would be delete, and username be the username, the cluster. So it would go ahead and delete the cluster, and if the directory, suppose if it is not empty, so it would throw you an exception that it would first of all give you a forbidden exception like HTTP 101 403 forbidden error, and there would be a remote exception would be there that the directory is not empty. So in that cases, first the file in the directory that needs to be deleted first, and then the empty directory could be deleted. So just make sure that you need to delete the existing file inside the directory, and then you can delete the entire directory. So file deleting operations, how to delete a file in through WebHDFS command. So basically that would be quite similar. If we need to delete a file through WebHDFS, so suppose I have a file called WebHDFS test.txt inside the WebHDFS new or WebHDFS directory which is residing within the HDFS platform of this cluster, and I'm trying to delete any file from HDFS inside a directory of HDFS through WebHDFS command. So I need to basically execute then 500 WebHDFS version 1 temp WebHDFS new WebHDFS test.txt. Suppose this file I'm trying to delete, which is residing inside the directory called WebHDFS new, and since I'm performing delete operation, so my op parameter should be delete, and the permission from the user this. So this command will delete a file inside the directory of HDFS, but the operation that I have performed here right now through WebHDFS. So that could be similar like this command if I need to perform through HDFS shell command, like grun through HDFS shell through rm of the file. So suppose if I'm deleting if I'm performing this operation through a normal HDFS shell command, so I could be doing like this. So I could be doing something like writing these types of commands if I'm doing the same operation through Hadoop FS shell command. So these are actually some of the commands that we have performed that in real time we need to do through WebHDFS, that's Hadoop REST API, but due to the normal standard operations on HDFS, but it's based using the HDFS REST API, Hadoop REST API, and this is the only some of the commands, the standard HDFS commands. This is the only way by which we could be able to interact directly with the REST API platforms while operating on the HDFS commands and operations. So basically WebHDFS is pretty much it provides a simple standard way to execute the Hadoop file system operations by an external client that doesn't necessarily run on the Hadoop cluster itself. So the requirement for WebHDFS is that the client needs to have a direct connection to the name node and the data node. So only the requirement to run in WebHDFS is that client needs to be connected with name node and data node of the cluster with the predefined ports. So clients of course should have the access to the standard web HDFS, the HDFS web UI. Of course they should have access to the URI access, like the IP address of the cluster along with the specific port number. Like you know that port number of name node is 50070, port number of data node is 50075, and port number of secondary name node 50090. But secondary name node is not it's not a concern for connecting through WebHDFS. Only the client should have a connection directly with name node and its predefined port number, that's 50070, and the data node also he needs to be able to connect with the port number 50075. So HDFS, this is the Hadoop HDFS over HTTP operation that was inspired by HDFS proxy and addresses it's actually those limitations that's by providing a proxy layer based on the pre-configured Tomcat bundle. So this platform was inspired by the HDFS proxy, which addresses the limitations by providing a proxy layer based on pre-configured Tomcat bundle, and it's of course going to be interoperable with WebHDFS API, but it doesn't require the firewall ports to be opened for the client. So of course this is going to be interoperable with WebHDFS API, but it doesn't require any time that the firewall ports that's also needs to be opened for the client. So it doesn't need any access to the firewall, but client needs to have access to the name node and data node URI and the corresponding port number to work with WebHDFS. So that was all about WebHDFS. Next, jump into MapReduce. So in order to start with MapReduce, let me first show you that how to go ahead and install Eclipse on a Linux cluster. So I have already. So for that purpose, you need to first download a Linux Eclipse for Linux first of all. So Eclipse for Linux basically you'd be getting directly from Eclipse website, that eclipse.org/downloads. Let me show you how to download this. So you just need to go ahead, go to this website, that's eclipse.org/downloads, and from there you just need to download the Eclipse IDE for Java developers. So for this is by default you'd be getting the Windows if you're accessing from Windows, but you should choose Linux and just select Linux 64-bit because Hadoop always works on 64-bit clusters. So you just go ahead and select Linux 64-bit edition of Eclipse. So next, what I need to do, we shut down this VM. So it's pretty simple to install Eclipse on Ubuntu. So the first command that you need to do after downloading Eclipse, so Ubuntu or CentOS or RHEL, whatever platform you are using. First you need to install, if you don't have Java or JDK installed, so just go ahead and install OpenJDK. So just type sudo apt-get install OpenJDK 7 JDK, and then you can download the Linux directly. Once you have you can just download Eclipse SDK, and if you have downloaded the Eclipse SDK, just go ahead and extract the SDK Eclipse package. So just unzip it, like type this types of command. tar.gz, just extract it. Once the file has been extracted, the next step that should be to create a desktop file that's called Eclipse desktop, that could be present within your user share applications. That, so you just need to create a desktop file. So just type first sudo vi and type user share applications and name it as eclipse.desktop. So it would create a new file that's being named as eclipse.desktop. Now within that file you need to make some entries, like I will show you. Let me put up the VM. I'll show you what types of commands you need to write. Just need to write these commands. Name as Eclipse, type would be application, execution would be what would be your the directory that where you have extracted the Eclipse. So if you have extracted, suppose I'm taking the example, you have extracted the Eclipse zipped package within opt or user local Eclipse probably. So just give the path of that location, and terminal, just make it false, and icon, just make the name, just give the location of the icon file, and comment is optional. No display would be false, and categories should be development IDE. Name you can mention as eclipse.desktop. So that's all. So these are the changes that you need to make. You first need to create a file eclipse.desktop and need to make an entry for those of the commands. So here in this cluster, what I did, I have already installed Eclipse. So this one is just to, this file is just to make a icon in your desktop for the quick launching purpose, and these are the changes that I have added. These are the commands I have added for the Eclipse desktop. Once I have added this, I'm able to see that Eclipse has launched in my desktop. So next thing is that how can I write a program first in Eclipse? So I need to double click it. Let me set up the workspace. So it has launched the Eclipse environment. So what I need to do next is I can click on new and select Java project. So first you can give a name for your Java project. So our first program I'm going to work. The first project that I am working is sample core Java. Next you can select your execution environment. So by default it should be Java SE 1.7. Click on next. Here you'll be able to see the Java settings, the source, the projects, the libraries. So here basically in MapReduce programming, in this step we need to add the external jars over here. So alternatively in Java programs as well, if we need to add external jar files, so we just need to click on external jar and we can just need to specify those jar files from here. So right now for the simple Java program, I don't need to add any external jar. So I'm just going ahead and click on next. And here in source under src, I'm first creating a package, giving a name as created a default package, and next I can create a Java class. So I'm creating a program on inheritance, a pretty simple program, just to show you how to write Java programs on Eclipse on Linux. So this is my simple program. So I'm going to write a simple example. So what I'm trying to do, first let me create a sample class, specify the variable, and calling a simple method. Here typing the output system.out.println. That's all. Next I'm creating a subclass of this class called A. So subclass could be B. An extends keyword specifies that the subclass whenever it extends from a superclass, specifying here a variable as k and taking a simple method solve. Next, inside the main class, I am defining the main method. So main method in Java is written as public static void main string args, and here just initializing my superclass, that's A, and creating object. Also initializing my subclass, that's B, with the new operator and creating object. So I was the variable that I'm initializing with a value, and also I'm initializing j, that was another variable with a value, and printing this output. Next line, subclass would have access to all public members of its superclass. So I'm calling the object of subclass, first assigning the values to them. And I'm just calling the methods. Just add a line system.out.println, just blankly it would just print a new line. Sum of I, sum of j and k in subobject. And finally, I'm calling the method called sum. So the sum method I need to define as well in my subclass. That's all. So what we did here, it's a simple example of a Java inheritance program, core Java inheritance program. So we have taken two classes, actually one class, that's the main class or the super class, and in the super class we have defined, we took up some variables I and j, and we have just implemented a method called show ij, where we have just showing the two variables, the values of the variables, and next we have created a subclass of from the main class, that's b, and here we have taken out a method where we are printing the values of the variable that we have taken for subclass, and also there is another method we have taken up called sum, where we're actually making a summation of the values of the three variables, that there were two variables from superclass and one variable that's from subclass. Then we have taken out in the main class, we have defined the main method, we have initialized the classes, that's the superclass and subclass, with the new operators. We have initialized those two classes, superclass, subclass. We have created objects, and after creating these objects, with the help of these objects, we have initialized the values within the variables of the superclass and subclass, and then we have just called the methods that we have defined within the superclass and subclasses. Simple program. So let's go ahead, save and run. Select run as, select Java application. So what it would show up, it would show up in output as, if you run this program and if the program runs successfully, so it would show up the output as contents of super object, that's I and j, the total the value, the summation value, actually the values of I and j, that's 10 and 20, and the contents of sub object, that's a subclass object, that's 7 and 8, k's value is 9, and then finally the output, that's for summation of these three variables. That's all. So it's a simple program, just a sample program. Let's see if we take out a small example from Java multi-threading. So multi-threading is pretty important because this utility we have been using mostly in our MapReduce samples as well, apart from generics and collections. So let's have a quick sample on Java multi-threading. So let's go ahead and select a class and give the class name as current Java thread demo. Can import Java package. Inside the class, just add main method, and call the main thread class. set a name of your thread. So I'm setting the name string. Then I'm taking a try catch block, an exception block. So try catch is basically for exception handling. So if we are facing any exceptions or errors, if we are thinking to face any issues or error, so we have been passing it through try block, and whatever the errors that we are expecting to catch, that we are putting towards a catch block. So in the try block, I am throwing a for loop. Then I'm calling the sleep method, thread sleep, so that my thread will be executed within the time interval that I'm specifying within the sleep method. Next, I'm giving catch block. Catch, I'm mentioning directly the exception block, which I'm expecting to face interrupted exception. So main thread interrupted. So that is my simple program. So what I'm doing here in this program is basically simply I've just created a thread in multi-threading environment of Java, and I have utilized for any multi-threading programming, I have to utilize exception block, that try catch block. So if there is any issues has been coming up during the thread executions and during the thread sleeping operations, so this exception will be caught out by the catch block. So let's go ahead and run the app. So to produce the output, so you can see that it has been the numbers are printed in just in 1 second interval, that's 1000 milliseconds interval, because I have applied here a thread sleeping operations. So there are a lot of programs are there you'd be getting in the document that I'll be showing sharing with you, and let's have a very quick program on Java collection. So in the Java collection, I'll be showing a program on hash set. So it would be very similar to key value programming for MapReduce. So let me show you the program. So basically, what is the hash set? So hash set is typically, it's an abstract class. So basically there are a lot of set classes are available in Java collection. So there is a linked hash class, a tree set class, etc. So you just can go through all of this through any standard core Java book. There is some operators being there like iterator, Java iterators, Java comparator. That's all are the part of Java collection package. Now our intention is basically to learn MapReduce. So just to make it easy to understand for you to understand in MapReduce. So I'm just going ahead and writing some of the simple programs, but I will not go in depth. I will share with you the document and you guys can go through it. So what I'm doing right now is basically to write a simple program on Java collection. So just take an example of Java collection using a storing user-defined classes in Java collection. So let me create a simple class once again. Let me give the name of the class as mail list. Importing the package util. First take a class. Defining constructor. Define a method. Here I'm using linked list and defining as the key pair as address, creating object as ML, let's add some element to the linked list. So I've added some sample data in the linked list. Now I can display the mailing list. And then add a space, a new line. That's all. So this program is about linked list in Java collection, and this program is just going to show that how to add the elements in the linked list through core Java. And we have utilized some standard function from Java.util classes for collections and generics operations in core Java. So there will be a list of the codes that will be there, which I'll be sharing with you. Just guys can go ahead and execute those programs, and that would be helpful for before starting the core programming on MapReduce. So let's go ahead with start the MapReduce. So let me close out Eclipse. Let me start the Cloudera VM. I hope all of you have downloaded the Cloudera Quick Start VM from their Cloudera website. So we would be performing the MapReduce programs first today on Cloudera VM, and then we can go ahead with our standard customized VM as well. So let me start with MapReduce. So first of all, we would go through the introductions of MapReduce. We would to check out how a MapReduce program works, what are the basic anatomies of a MapReduce jobs run, what are the basic steps for MapReduce jobs, what are the common failures in real time that we face in day-to-day operations as developers, what are the job scheduling process, what are the various phases for MapReduce like mapper, reducer, shuffling, sorting, what are the task execution process, etc. And then there is a lot of things that's to cover up, like MapReduce types and formats, the various features on MapReduce, MapReduce version 1, MapReduce version 2, what is Yarn, how Yarn works, and its architectures and all. So what are these objectives for the behind this module that we'll be first of all we'll be explaining the concepts of MapReduce. We will be list out the steps that we have already gone through, the steps of installations of Hadoop, and also we'll be talking about the roles of users and systems. So how these concepts of MapReduce came into the Hadoop paradigms, and what are the various factors that influences MapReduce. So basically, we have already talked, we have seen a sample MapReduce jar files already. So right now we're just going to write the programs on our customized MapReduce jar file. So before going through that, what is actually is MapReduce? So whenever you run a MapReduce job with a single method called submit method that we call on Java or Python or C#, any other languages. So typically there are some objects by which we could be able to perform the MapReduce job. So one of the object or class is called job object, which is being utilized to call up a job, to submit the job, and to execute the operations for MapReduce. So basically, in the releases of Hadoop package after the including 0.20 releases, during MapReduce jobs operations, there are a few points was there that was taking up the MapReduce implementations. That one of them is mapred.job.tracker, which is actually the course MapReduce services, and that is actually the was a configuration property that we need to set to local, and that is a default property. And then when the local job runner is going to be used, so that runner runs actually the whole job in the single JVM. So it was actually designed for testing and running the MapReduce programs on small data sets. Next, in MapReduce, in Hadoop version 0.2.3 onwards, a new MapReduce implementation was introduced. So that new implementation is called MapReduce 2, which is actually built on the system called Yarn. So just for now, we will be first talking about MapReduce property, that's MapReduce 1, and also, of course, we need to talk about MapReduce 2 or Yarn. So basically, for Yarn onwards, whenever we started to work with Yarn, for Yarn onwards, during configurations of Hadoop, we need to write in mapred site.xml that we have already gone through. In this configuration of mapred site.xml, we need to mention the exact node value for MapReduce as mapreduce.framework.name, and which actually takes care of the values for local. That's for the local job runner. If you are working on classic MapReduce, it would be value should be as classic MapReduce work, which is also known as MapReduce. But in both of the cases, job tracker and task trackers, that's are going to run. So job tracker and task tracker, job tracker is a master service for MapReduce, and task tracker is a slave or worker services for MapReduce. So basically, there are also some important features are there for MapReduce itself. We go through. So MapReduce is typically it's a programming model, and it has its associated implementations for processing and generating the large datasets over the parallel and distribution algorithms on the Hadoop cluster. So typically a MapReduce operation, it includes the features like a map function and reduce function in the program, so which specify actually the computation in terms of map and reduce. So actually MapReduce is the original compute section in Hadoop cluster, and it follows basically the implementation properties of a mapper, which actually maps the jobs which is being submitted into the cluster after the data has been submitted through HDFS. Then the computation starts actually through MapReduce programs. Yes, there is a question from Nora. com.hadoop.training.java. No. It's not a default package. It's not a default package. It's that was the user-defined package. That was the user-defined package that I created for the demo. That's the user-defined package that I created for the demo. So it's nothing as inbuilt package. Okay. All right. So the second job that actually what MapReduce performs is a parallel computations across the large-scale clusters of machines, and also MapReduce is also responsible for handling the failures. So during the computations, during the executions of the job through MapReduce, if there is any errors, issues coming up through data, through job processing issues, or through the cluster issues, that every issues or the failures that regressfully it needs to be handled by MapReduce platform. So any sorts of machine failures or performance issues, everything that needs to be handled by the MapReduce. And also MapReduce needs to ensure that there should be an efficient communication between the multiple nodes. So normally in the production clusters in real time, we need to work where the nodes that might be ranges, row numbers might be ranges from 10 to 30 or more than 30, that 50, 100 nodes we need to work at a time. And while the MapReduce job is being running in real time across the multiple nodes, so MapReduce need to make sure that all the jobs are running smoothly across all of the clusters. I'm not able to speak because it's showing organization it had been. Okay. I have not muted actually anyone. Let me see. Yeah, I have unmuted everyone. So Nora, if you have any questions, you can ask me.
Yeah, I'm able to hear you now. Yeah, yeah. Thank you so much.
Okay. So what I was talking about that about MapReduce features and the basic functionality of MapReduce. So basically, MapReduce has two different paradigms. So older versions of MapReduce, which we call as classic MapReduce or MapReduce 1. So that was actually the features whenever the job needs to run in classic MapReduce. Just like as a highest level, there were the four independent entities was there. Basically in classic MapReduce, what we used to see earlier than Hadoop packages of 0.23. In classic MapReduce, always we need to have a client which submits actually the MapReduce job, then the job tracker who actually coordinates the job running process. The job tracker is basically a Java application whose main class is basically the job tracker. Then comes a task tracker or the worker classes, so whose basic task is basically to run the job that has been split it into. So task tracker actually the worker services Java applications whose main class is task tracker, and fourth is a distributed file system, that HDFS, which is used to share the job files between the other entities. So that is the four independent processes and the services entities that's being running in the classic MapReduce. That's in the MapReduce phase 1, MapReduce version 1. So, or you can say as older MapReduce. So as an analogy wise, usual manual vote that's been counting after as an election as an analogy. So normally what happens, like just for a real-time example, whenever the data has been submitted through the polling election cases, election time, the data has been submitted through the different booth ballots, and through the teller machines, the votes has been going to submit over the different through the different machines. So in the next phase, in the poll count, it is being happening through each and every booth. So after the data has been ingested through that each and every through the tellers machines into the main servers. So after that, in the next level, in the mapper phase, actually the data is going to be mapped. It's going to be uh, it's need to be mapped to the specific based on the specific keys and the values, and they're actually in the MapReduce context, they're actually the shuffling and sorting phase going to start. So first of all, a map phase is going to occur, and after the mapping phase, where the data has to be mapped first of all based on the keys and common keys and values, and after that the data is after the mapping phase, it's being entering through the shuffling and sorting phases, where the data which are based on the same key has been acquired in one place. Next, the other data which are acquired through the another key value, that has to be separated in other side like this way. So actually this phase is being resembles to the shuffling and sorting, and then there comes an intermediate phases that's an shuffling sort, which is an intermediate phase, and after that, after the end of the map phase, actually the reduce phase is going to occur, where in normal practical cases of election case, if we just take an example, like where exactly the total count is being happening, how many total votes has been acquired by each and every candidates. So this is actually going to be the introductions of the reduce phase in MapReduce. And after the reduce phase, where all the jobs or all the data has been percolated, the actual calculation has been done. So finally, the end of the reduce phase, the total election results has been declared. So this is this a simple MapReduce jobs analogy has been defined in terms of a normal real-time example. So what you can conclude, like in analogy format, that the key reason to perform this mapping and reducing is basically to speed up the execution of a specific process by splitting the process into the number of tasks, so to enhance some more parallelism. So parallelism means we can be able to do multiple phases, multiple work at the same time, but simultaneously we can do a lot of different works. So parallelism also, it has been enhancing towards the asynchronous jobs and asynchronous work. So make sure that normally MapReduce jobs in version 2 onwards, all the jobs that we run through MapReduce, that's all works in an asynchronous manner. Means that that's the jobs that's going to occur, they are all being occurring through the they're not dependent on each other. So the mapping phase is going to occur, and at the end of the mapping phase, the output of the mapping phase just comes into the reduce phase. So if the data is not coming properly, so mapper doesn't wait for that. Mapper just continuously working, and they're just been gathering the data that's coming out from HDFS and starts to work on that. Similarly, reduce phase, the reducer, it has also starts to work the data that's been coming out, whichever data has been coming out from the outputs of mapper, and starts work on that. So there is no intermediary halting in between the two steps. Now actually what is happening while the job submission process has been going on? So actually in parallelism types also, whenever the job submission is going to occur, so basically the job submission process has been implemented by job submitter function. So job submitter actually does the following. First of all, it asks the job tracker, the master service of MapReduce, for a new job ID. If suppose whenever a new job has been submitted, so it just by calling get new job ID method on the program on job tracker. Now then it checks the output specification for the corresponding job. For example, if the output directory has not specified, or if it is already it already exists, so the job is not submitted, and in that cases an error has to be thrown by the MapReduce program if suppose no job has been submitted. Now next phase is that it just go ahead and compute the input split for the job. If the job is submitted, it would then start to compute the input split for the job, and if the split that cannot be computed because of some input paths doesn't exist, for example if the job is not submitted, so in that case an error would be throwing to the MapReduce program. But if the job is submitted, then the copy is actually it would just go ahead and copy the resources that's needed to run the job, including the job jar file, the computation file, the configuration file, and the computed input splits. So the job trackers file system in a directory that's which needs to be named after the job ID. The job jar that will be also copied with a high replication factor, so which defaults to 10 mostly, so that there could be lot of copies that could be available across the cluster for the task tracker to access when they run the task for the job. And finally it would tell the job tracker that the job is ready for the execution by calling the submit job on job tracker. And also there are specific phases that is being available for a typical MapReduce job to work. The first step is called the job initialization. So job initialization is pretty much like whenever suppose first time job tracker receives a call to its submit job method, that whenever a job has been submitted, and it puts out into an internal queue from where the job scheduler will pick up and initialize the job. So job initialization, again, it involves like creation of an object to represent the job that's being going to run, which encapsulates its task, and several bookkeeping information to keep track of that, whatever the task status and progress. Now in order to create basically the list of the task that's going to run, the job scheduler first retrieves the input splits which needs to be computed by the client from the shared file system, and it then creates one map task for each and every split. The number of reduced tasks on the other hand just to create is to determine by the MapReduce.reduce.task property in the job, which is again need to be set out by the setNum reduce task method. Now again the job scheduler, it just simply creates the number of reduced tasks that needs to be run, and the tasker also has to be given ID at this point. In addition to the maps and reduce task, two further tasks are created. One is called the job setup task, another is called the job cleanup task. So this task needs to be run by the task tracker, and they are also used to run code to set up the job before any map task could run, and to clean up after all the reduced tasks are being completed. The output committer is needs to be configured for the job, which could be able to determine that the code that needs to be run, and also by default if there is a file output committer is being available. So for the job setup task, it will create the final output directory as well for the job, and the temporary working space for the task output. And if suppose a job cleanup task, it will during that time it will also delete the temporary working space for the task output and all. So that's the exact situations, that's what's happened during the job initialization time. The next phase is called the task assignment. So if I just make a list of the phases for MapReduce, phases of MapReduce, number one is job initialization. Number 2 is going to be the task assignment. So what happens during task assignment? So task trackers, actually they are running a simple loop that periodically sends the heartbeat method calls to the job tracker. Now heartbeat actually tells the job tracker that a task tracker is alive, but they are also double as a channel for messages. So as a part of the heartbeat, what happens that the task tracker will indicate that whether it's ready to run a new task, a new job or not. If it is able to run, the job tracker then will go ahead and allocate a task to the task tracker, which is able to communicate by which it could be able to communicate to the task tracker using the heartbeat return value. Now before it can choose a task for the task tracker, the job tracker must choose a job first of all, which is being submitted in HDFS to select the task from. So there are various scheduling algorithms are also there by which the default one the job has to be scheduled, and the default one is simply to maintain a priority list of the jobs. So once the job has been chosen, the job tracker chooses a task for the specific job. Task trackers, on the other hand, they are having a fixed numbers of slots for map task and for reduced task. So for example, a task tracker um, MapReduce slots, if I take the task tracker, they always have a fixed numbers of slots for the map task, fixed numbers of map task, and for reduced task. So for example, like a task tracker may be able to run 2 map tasks and 2 reduced tasks simultaneously, and that could be also able to precise the numbers of cores and the amount of memory that could be assigned to the task tracker. So the default scheduler files, that could be an empty map task slots before reduced task slots. So if the task tracker has at least one empty map task, so the job tracker will select a map task, otherwise it will select a reduced task. So to choose the reduced task also, the job tracker simply takes the next in its list that is yet to be done, the reduced task. So since there is no data locality consideration for a map task, however, it could able to take the account for the task tracker's network location and could be able to pick up for the task whose input split is as close as possible to the task tracker. In optimal cases, the task is basically the data local, so that could be able to run on the same node as where the split going to be reside. Alternatively, the task may be the rack local as well on the same rack, but may not be on the same node as a split. So some tasks are neither data local, some tasks are neither nor the rack local. They could be able to retrieve the data from the different rack from the one that they are running. So you can tell the proportions of each types of the rack by just take a look on the job counter. The third step is basically, it's called what is called as a task execution step. So this phase is called the task execution, where basically the executions of the task is going to occur, and in this phase now the task tracker is already having assigned to a job for a task. So the next step is basically to run the task. So first of all, it localizes the job jar by copying it from the shared file system to the task tracker's file system, and it also copies any of the files which is needed for the distributed cache from the distributed cache by the application local disk. Distributed cache I will be explaining maybe in the next module, and also secondly, it also being able to create a local working directory for the task, and then it just go ahead and unjar the content of the jar into the directory. And thirdly, it would create an instance of task runner to run the task. So task runner, actually it's nothing but it just launches a new JVM to run each and every task, so that if there is any bug in the user defined maps or reduce function, it would not affect to the task tracker. And however, it could be also able to possible to reuse a JVM also as the same JVM between the task. The child process, on the other hand, it could be able to communicate with the parent process through the umbilical interface, and this is where it could be able to perform the parent of the task progress. It could be able to check in each and every few seconds until the task is going to be completed. Now also the final step would be the progress and status update. So in progress and status update, like MapReduce jobs, actually the long running batch jobs. So just being taking anything from minutes to hours, it being takes a job to run. And because this is a significant length of time, it's important for the user to just go back to the how the job is being running, how the job is being progressing to check. So a job and its each and every task, they always have a status. So which includes like such things that's the state of the job or the task, like whether it's running successfully or completed or failed, such things we could be able to check. So the progress of maps and reducers as well, the values of jobs counter, the status messages or descriptions which may be set by the user code. So this status, they are also changing over the course of the job, and also that just to show that how they can communicate back to the client. So whenever suppose a task is running, it always keep track of its progress. That is the proportion of the task, how much it has been completed, and that's actually the proportion of the input that's actually going to show that how much proportion of the task has been completed. So just for map task, that could be the proportion of the input file that has been processed, and for reduce task, that is could be more little bit complex, but the system can still estimate the proportions of the reduce input that is going to be processed. It actually does so by dividing the total progress into the three parts, so corresponding to the three phases in the shuffle. So for example, like if the task has run the reducer on half of its input, then the task progress would be just fifth out of 6, and since it has completed the copy and sort phases in 1/3 each of them, and in a halfway through the reduce phase of 1/6 of each of them. So here basically there is a sample example has been given from word count sample jar file we have already executed on MapReduce. So here there is being assumed that there are some sample input data file has been supplied, like some sample sentences has been like the quick brown fox jumps over the lazy dog, a dog is man's best friend, like this types of input data has been there, and we are being able to we are going to perform a MapReduce job word count example on using this data. So what would be the phases of that in that cases for the MapReduce? So input would be just like this, the sample data. In the splitting phase, the actual data is getting to be divided. Now here comes actual first mapping phase, where each and every sentences wise the keys will be specified, that how many words are there, and what are the occurrences of each and every word. That's being counted in the mapping phase. After the mapping phase is going to after the end of the mapping phase, the outputs of the mapping phase is going to be entered into the intermediate phase called shuffling. So in the shuffling phase, actually the actual job intermediate steps, like the actual counting of the jobs that's going to start. Now MapReduce also always makes guarantee that the input to the every reducer that could be always sorted by the key, and this process by which the system actually performs the sort. So that's the shuffling and sorting. So, and it could be also able to transfer the map outputs to the reducers as an inputs. So that is called as shuffle. Now if we take that how the shuffle is being working, so there is also a little bit of basic understanding would be helpful just to understand that how to optimize a MapReduce program. So basically the shuffling is actual the area of the code base where the refinements and improvements are continuously that we could be able to make. And actually in the shuffling phase, we could be able to make the performance tuning of the MapReduce job. We could be improve the MapReduce programming time, the job runs details that we could be able to do. So there are always various phases for the shuffling and sorting. Like the map side, we can make our changes. In the reduce side also, we could be able to make the changes. So as you can see in the shuffling phases, actually we have been making our divisions about the occurrences of these words, and finally the outputs of the shuffling phases has been taken as an input of reducing, where actual the word-wise word as well as sentences. So in a particular sentences, the word-wise word we have been counting up, and finally the outputs of the reducing has been taken out as an output of a MapReduce job. So this is a high-level overview of this MapReduce operations taking up a sample data. Now actually how this execution is going to occur. So first of all, the map phase is going to be consist of the following phases, like the map phase, then comes the partition phase, then the shuffle phase, and then sort phase, and then comes finally the reduce phase. So might be getting confused that whether the partition phase is always going to occur before the map phase or after the map phase. Just being make sure partition phase always going to occur always after the map phase, and shuffle phase can never be occur without the partitioning is being happening. So in the map phase, what happens, actually the jobs is going to read the assigned input splits from the HDFS, and based on the job reading operations been going to occur, it also able to parse the input data into the several records, like through the key value pairs. Now once the key value pairs, I mean the input data has been processed, so it being able to apply the map function to each and every records as well, and same time it would be able to inform the master node about its completion status. Now in the next phase, in the partition phase, what's going to occur, like each mapper that must be able to determine like which reducer will receive each and every output, and based on that, for any of the key values, the destination partition could be the same. And in the partition phase, actually it's going to determine like what would be the numbers of partitions that could be the equals to the numbers of reducers. And what is happening in the shuffle phase? So actually in the shuffle phase, it's able to fetches the input data from all of the map tasks for the corresponding portions to the actual reducer bar task packet. So whatever the data, whatever the input jobs is being coming out from the outputs of the partition phase, that is actually going to be the inputs of the reduce phase. And next in the shuffle phase, it's actually just go ahead and take all this input data from the maps and portions and mapping to the input of the reducer. And after the shuffle phase, there is another intermediate phase is there, that's called sort. So in the sorting phase, actually the merge sort will happen. Merge sort is a typical data structure algorithm. It's just being based on that algorithm itself. The merge sort will all of this map outputs which is coming out from the shuffle, and it being taken as an input to the reduce phase in a single running operation. And finally there comes in the reduce operations. So in the reducer operations, actually it would be applicable to the user defined reduce functions to the merged run, and based on that it could be able to pass the keys and the corresponding list of values. And in this way, after the end of the MapReduce job, the final output would be written to a file on HDFS. So what is actually happened during the map task or the reduce task? So basically on the map side, whenever the map function starts to produce the output, it is not simply written to the disk. It is the process is being more involved and takes advantages of buffering the writes in memory and doing some processing for efficiency. Like if each map task has a circular memory buffer and that it's being able to write the output, the buffer suppose is 100 megabytes if it is by default. So there could be a size that could be tuned by changing to the io.sort.mb property, and when the contents of the buffer reaches to a certain threshold size like 80% or like that, so there will be a background thread would be working that will start to spill the contents to a disk, and map outputs then will continue to be written to the buffer while the spill takes places. But if the buffer fills up during the time, so the map will block until the split is being complete. Now before it's being able to write to the disk, the thread would first divides the data into the several partitions as well, which is corresponds to the reducers by which it will ultimately being sent to. So within each and every partition, the background thread also will perform an in-memory sorting sort by key, and if there is a combiner function is also running, so it could be able to run on the output of the sort. So running the combiner function, that would also it would make makes more important. And for the reduce side, how the reduce is being going to occur, the map output file, if it is sitting on the local disk for the machine, that is on the map task, but now the make sure that map outputs always get written to the local disk. So reduce our outputs, they may not be written to the local disk, but right now it's being needed by the machine that it's about to run the reduce task for the partition. So furthermore, the reduce task also needs the map output for the particular partition for the several map tasks across the cluster. The map task may finish at the different times, so the reduce task always starts by copying their output as soon as it is going to complete. So that's why the copy phase of the reduce task is basically so important. So the reduce task has a small numbers of copier threads so that it can fetch up the map outputs also in parallel. The default is always works it on 5 threads. Now the number could be also changed by setting the mapread.reduce.parallel.copies property. So there are specific task execution environments are there, and there are some specific properties are there for configuration tuning purpose. So suppose this is an example has been given on the map execution which is being distributed across a two-node environment. So MapReduce actually executed in a distributed two-node environment. One environment, just one in the node 1, suppose, when the file has been loaded from the local HDFS stores, and then actually the partitioners is going to occur after the mappers, and sorting, reducer, and output formats work. Just go ahead and work in the input format. And so similarly, in just example, we could be able to see that how the mappers on each and every nodes, they're having assigned to the specific input format blocks based on the input format on the data of the MapReduce program. The record reader just being reads the splits, each and every data splits as a keys and their values. So values has been assigned always based on the specific key. And map function is always having been applied. So as you can see here is after splitting, the map functions is going to occur, which is applied each and every record to return 0 or more new records. And intermediate outputs are always must be stored in the local file systems as a file, whichever coming as an output of mapper, and it is always being assigned to the records of the reducer. Now, in between the mappers and actual reduce, there is always the intermediate functions is going to occur through the intermediate key value pairs. There comes an outputs of mappers always stored in the partitioners, and in the partitioner phase actually going to start the intermediate phase called shuffling and sorting. So whenever the partitioning phases is being started, the partitioner is being started to work, actually that time itself shuffling and sorting is going to occur, which is actually the intermediate key value pairs exchanged by all of the nodes in this step. So the key value pairs actually is going to sort it out by their keys, and after that, the end of the shuffling phases, the outputs of shufflers is going ahead to enter into the reducer. So in the reducer itself, actually the final processing is going to occur. So once the reducer has completed its job, then the output from the reducer, again final key value pairs, it is being written back to the local HDFS store for the specific output format. So this is actually map reduce execution is going to occur. So which just being main has been described about the mapping phase. Next, we can be able to define what are the essential cases for MapReduce phases. First of all, the input specification has been given in the key value pairs, and a user-defined map function is being always applied to each of the every input records to produce a list of the intermediate key value pairs. And finally, this user-defined reduce function is again have to be called once for each and every distinct key in the map output. So the list of the intermediate values always have to be associated with that key that's being passed. So a job is typically a full MapReduce program, so which typically will cause the multiple maps and reduce functions to be running in parallel over the entire life of the program. And what is a task? A task is a map or reduce function that is being executed on a subsets of data. So make sure that you need to know the differences between a job and a task. A job and task is not the same, both are different. A job is a full MapReduce program, whereas a task is actually the maps and reduce function that's being executed on several subsets of data. Now, actually, the functionality wise, the differences between job tracker and task tracker. The job tracker is being able to run as a master node. It's being working as a separate node. It's being able to manage of the full cluster for MapReduce operations. It's being able to take the job request from the client, divides the job request into the task and the schedules, and assigns the individual task to the slave nodes. And always job tracker is a single point of failure. What is a task tracker? Task tracker is a slave node. So it's being manages each and every active task, and it's being able to communicate regularly with the job tracker. So if I just need to talk about the basic MapReduce engine, that's how this execution wise. So always Hadoop provides basic information to the maps and reduce task about the environment in which it is being running. So always a map task can discover the name of the file where it's being processing, and a maps or reduce task can also find out the attempt on the numbers of tasks that's being going to execute. So the basic properties that could be accessed from the job configurations that could be obtained in the old MapReduce API by providing some of the implementations, some of the functions we could be able to utilize, like configure method on the mappers and reducer, where configuration is being passed as an argument. So basically, in this context of config, so if you just pass the config method within the mapper or reducer class, so you'll be able to see there are some of the properties that could be able to visualize, like mapred.job.id, which specifies like the specific job ID, the MapReduce job ID. Then you could be able to see mapred.tip.id, MapRed.TID actually the task ID. Then MapRed dot task.id that specifies the task attempt ID. So there is a difference between a task ID and task attempt ID. Task ID is actually the ID assigned to a task, and task attempt ID means how many times the task has been attempted. Then comes the value called partition. So partition means the index of the task within the job, MapRed.task.partition, and then called MapRed.task.is.map. That means that whether the task is a map task or not. So that value specifies. So whether the corresponding task is either a map task or not. So and there are also some of the streaming evolution environment variables that also configured. So this is how we could be able to configure the configuration environment of a mapper and reducer. So how exactly the MapReduce engine is going to execute? So basically the job tracker and task tracker, they are actually the responsible services for performing the MapReduce operations, and generally the job tracker is always being present as a master node of the Hadoop, and the task tracker service always being working as a worker or slave node of the Hadoop. The job tracker service is responsible for assigning the jobs to the data node, and the data node always being consists of the task tracker, which performs a task that's submitted by the job tracker, and it always provides the results back to the job tracker. So some of the MapReduce and their associated tasks, like if we could make a list of that, map process is an initial ingestion step, like where the job is being assigned, and according to the job submission cases, the corresponding task is going to be executed. It's first going to be initialized, and once the map process has been started, the transformation step, where individual input records that could be processed in parallel. Now next step of the map is a reduce process, which is nothing but is an aggregations, or is in short we can say as a summarization step, by which all the associated records that could be processed in a group order. Now task trackers actually the worker nodes, which is being responsible for task execution, task initialization, assignments and all. So they have been just keeping track of the individual map task, which could be run in parallel, and a map job always runs on a particular task tracker on a slave node. Job tracker on the other hand, it also keeps track of a typical MapReduce job. And in short, it always communicates with the task trackers to get status of the job completion, and correspondingly it allocates to a particular task to a task tracker node. So how the Hadoop job flow is being working with associated with HDFS. So whenever the client submits the job through the job tracker or the name node, so the client always can interact with the master services. Client can never interact with the slave or worker services directly. Client can, whenever client submits the job, they can interconnect with either the job tracker on the name node, and job tracker and name node just being able to assign their jobs for the configuration side, for data storage and compute side on the corresponding task trackers and the data node. So whenever the job is going to execute in the interaction side, first of all the job is going to submit it through the name node. The data has been submitted, and the data has been blocked into the several chunks, and HDFS data nodes has been taking care of that. Next, job tracker has been assigned a particular job. It is being make it aware of that a new job has been submitted, so job tracker can start work on that. So that's during the job submission process, Hadoop MapReduce job is going to be submitted by the client in the form of input file or a number of input split of files that's been contains the data. Now next phases is going to occur during the distributions of the input split, where the job tracker actually distributes the input split to the separate task trackers. In the next step is just nothing but the coordinations with the task trackers, where the job tracker coordinates with the several task trackers, just taking up a healthy task tracker, that which task tracker is sending the most healthier heartbeats. Based on that, it assigns the jobs to the corresponding task tracker. And if suppose any of the task tracker is not being able to send the heartbeats properly on time, not with the proper job IDs and all, so in that cases the corresponding task tracker is going to be blacklisted, and it not being able to work for more than 2-3 hours based on the health status of the task tracker node. So once the job tracker finishes the assignment of the corresponding healthy task trackers for job execution, then it first starts to assign the jobs to the task tracker after coordination. And if any cases like the job submission cases from the task trackers is being fails to take the job, then there is a resubmission is going to occur. There's a resubmissions of the task. So job tracker again just go ahead and resubmit the task to the alternate task trackers if suppose the data node failures occur, or if suppose if the task tracker was not connected properly, or it was not online at that time. So it's going to be job tracker will go to resubmit the process. And finally it being go ahead and take up the interaction decision that whether the job has been executed successfully or there is a failure. So success or failure status. So job status always gathers the final outputs and informs the client that with the corresponding success or the failure message. So what are the basic characteristics for Hadoop MapReduce? So basically, some of the basic characteristics of MapReduce, like it handles a very large data like from terabytes to petabytes to exabytes data and so on. It always works on the principle like write once, read many times. So a MapReduce job is not something like each and every day we need to write the same MapReduce job for the same execution. No, we write MapReduce jobs mostly for one specific operations once in a time, but we can read multiple times from those programs. We can execute those jar files, MapReduce jar files. Once we have written that jar, we can execute it and utilize it many times. It always allows for the basic parallelisms without mutexes, always works on asynchronous principles. The maps and reduce, it's typically these operations that's being performed by the same physical processors, and these operations are always need to be provisioned near the data. So as we have mentioned in the first time that Hadoop architecture is always based on economic purposes. So it works on commodity servers, and always it based on the principle that there is no unnecessary data movement is going to occur, so that it would be increasing the cost. So always the MapReduce jobs being working on top of data. So data doesn't need to be moved towards the MapReduce engine. Always MapReduce jobs, the task tracker, job tracker works on top of data. So there is no unnecessary data movement is being supported by this architecture. So that's why the commodity hardwares and storage are always getting to be leveraged, and the runtime, the exact runtimes of MapReduce, that's actually takes care of splitting and moving of data operations. Some of the real-time users for MapReduce, like there are always being MapReduce simple algorithms are there, which we will be also trying to on our next classes, like as the grep, text indexing, reverse indexing. We'll be also checking some of the sample algorithms. There will be always performing a data-intensive computing such as shuffling, sortings. Data mining operations would be also there in algorithms for MapReduce, like Bayesian classification. You can just have a look on that about Bayesian classification, are very important data mining algorithms operations. Search engine operations like keyword indexing, rendering, page ranking facilities, enterprise analytics, semantic web and web 3.0, and Gaussian analytics for locating the extraterrestrial objects in astronomical cases. So in those of the real-time use cases, always MapReduce is a common sample solution that's going to occur, going to execute, of course. So and we have already gone through the steps of Hadoop installation. So what will be given, you'd be getting sample Hadoop VM, as I mentioned very beginning, that all of you that would be getting a plug and play Hadoop deployed server. It would be an Ubuntu server where you'd be having a single node Hadoop cluster would be installed. Also, you'd getting a lot of data, sample data you'd be getting, like this types of data like Gutenberg data, then weather data, weather API specific data, geographical data, sensor data. That's some of the sample data would be there. And also all of the specific packages like Hadoop, Pig, Hive, Scoop, Flume, Storm, Kafka, that's all would be installed over the VM, so that you guys can go ahead and start direct programming on the VM and with all the sample data set. So I'll be sharing with the VM details very soon with you. And so what are the steps that to build a MapReduce program? So basically the steps to build up a basic MapReduce program, like first of all you need to determine that if the problem is parallelizable and it could be able to solvable via MapReduce. Then accordingly you need to first design the algorithms and implement the solutions using mapper and reducer. You need to also compile the source code with core Apache Hadoop. you need to package the code as a jar as executable. So basically packaging in during building the jar file, any times when we need to package the jar file from a Java code, we can use either Ant or Maven. So it's just being up to you which tool you'd like to utilize. So you need to package the code, your Java code, your MapReduce code as a jar, executable jar, and then you can configure the application job to as a numbers of mappers and reduce a task and input output streams. Finally, you could be able to load the data, and next you can just able to launch the job and monitor and the result. So some of the basic requirements for Hadoop MapReduce, like the user or developer, they always require to set the framework for the parameters, like the location of the job input for the file system, the locations of the job output in the file system, and then they need to specify the basic input format, output format of the job, and the classes which are containing the map functions, and optionally the classes that switches being containing the reduce functions. And in any cases, suppose if the job doesn't need to have a reduce function also, there is no need to specify a reducer class. So it is always a cost optimal approach in MapReduce. So whichever the functionality is not needed, we can skip that. If the framework always utilize a utility called partitioning of data. So there would be the framework will implement a partitioning of the input, schedule, execute the map task across the cluster. If it is requested, it can also sort the results of the map task, execute the reduced task with the map output. And finally, the map output will be moved to the output directory and job status will be reported to the user. So we have done till now with the jar file. Directly we have started to work with the jar file on the data, and we have started to execute the jar files to build a MapReduce execution and take out the output. But right now we need to build out our own jar file, so that's why we need to code a MapReduce program. Now, what are the basic features of MapReduce? Like MapReduce always uses our key value pairs. Key features of Hadoop MapReduce, like it uses the framework always utilizes each record of input into a key value pair, which is a one-time input to the map function once. The map output is also set of a key value pair, which is grouped and sorted by key. Reduce functions, on the other hand, is called one time for each and every keys in sort sequences with a key and set of the value that could be able to share that key. The reduce method maybe also take an output and an arbitrary numbers of key value pairs which are written to the output files in the job output directory. So the framework always provides two processes that can handle the management of the MapReduce job. The task tracker that actually manages the executions of the individual maps and reduce tasks on the compute node, and job tracker actually takes care of accepting the job submission, provide the job monitoring, and manages the distributions of the tasks in the task tracker. Now, one very important concept is there for MapReduce, that's called the speculative execution. So what is meant by speculative execution in MapReduce? So actually the MapReduce model is utilized to break the jobs into the task and run the task in parallel to make the overall job execution time smaller than it could take. Otherwise, it could be just like a time consuming if the tasks are running sequentially, and this makes the job execution time sensitive to the slow running task, and it takes only one slow task to make the whole job take significantly longer than it could have done otherwise. So whenever a job consists of suppose hundreds or thousands of tasks, possibly there could be a few straggling tasks. It's very real. So task may be slow. Maybe a MapReduce task always it could be slower for various reasons. So including like hardware degradations or software misconfiguration or bad code. So but the real causes that could be hard to detect since a task will still complete successfully. So in real time when the developers need to work mostly to performance tuning of the MapReduce jobs, and to make sure that job could be able to run more faster, it could be more optimized and all. So Hadoop doesn't try to diagnose a fixed slow running task. Instead of that, it always tries to detect when a task is running slower than expected and launches another. So equivalently, just task can take a backup. So this is termed as speculative execution of task. So in the speculative execution, it's important to understand that speculative execution doesn't work by launching the two duplicate tasks at about same time. So it never works. Two duplicate tasks at same time. so they can race each other. There could be the wasteful of the cluster resources. Rather than that, a speculative task always launched only after all the tasks for a job have been launched, and then only for the task for a job have been launched, and then um, that have been running for some time, those whichever the jobs which has been running for some time, at least for a minute, and have failed to make much more progress. So on average, as the other task from the job that has been running, so whenever a task completes successfully, and whenever the task always if it is completed successfully, any duplicate task um, which are running, they are killed since they are no longer needed. So if the original task it completes before the speculative task, so then the speculative task is killed. On the other hand, if the speculative task is finished first, then the original task is killed first. So speculative execution is a one type of optimization. It's not a feature on a job, of a MapReduce job. So speculative execution always is a type of MapReduce job optimization. So it's not a feature to make the jobs running more reliably. If there are bugs that sometimes causes a task to hang or slow down, then relying on speculative execution just to avoid these problems is unwise. So it won't work reliably, since the same bugs are likely to affect the speculative task as well. So you should first of all fix the bug in the code so that the task wouldn't hang or slow down during execution. So speculative executions, it can be turned on by default. It could be turned on by default, and it can be enabled or disabled independently for map task and reduce task on a cluster basis or on a per job basis. So these are the properties for speculative execution. So these are the steps that there is a good case to always being turned off the speculative execution, for turning off speculative execution for reduced tasks specifically, since any duplicate reduced task, they have to fetch the same map outputs as the original task, and this can significantly increase the network traffic on the cluster. So these are one of the case scenarios that where we need to turn off the speculative execution. Now basically the goal for speculative execution is to reduce the job execution time, but this comes always at the cost of the cluster efficiency. On a busy cluster, speculative execution can reduce overall throughput, since a redundant task has been executed in an attempt to bring down the speculation time for the single job. So for this reason, some cluster administrators, they prefer to turn it off on the cluster, and they can have users explicitly turn it on for their own individual job execution purpose. And another reason that when the speculative execution is turned off is for the tasks that are not idempotent. So, however, in many cases that is possible to write the task that could be idempotent, and an output committer, they could be able to promote the output to the final location when the task succeeds. So there is being always some task side effects as being there, task JVM reusing cases as being there, for which we could be able to do that. So actually we have been defined MapReduce processes. Okay. Okay, so there is a question that is there any way to turn on the speculative execution? So as I said that speculative execution always has to be turned on by default. There is no such way that you could be able to turn it you need to turn on, or just by using some specific configuration. It could be always being turned on by default, but it could be enabled or disabled independently by the map and reduce task, and specifically on the code side. So basically there are a few properties are there. Let me show you. There are specifically some properties are there for speculative execution. Number one is mapred.map tasks dot speculative properties. So it's a Boolean type property. Its default value is true. It specifies whether extra instances of the map task may be launched, or if a task is making slow progress to check. Another property is called maprate.reduce.task.speculative execution. So it's also a Boolean type of value. It's just mentioning that whether an extra instances of reduced task may be launched, or if a task is making the slow progress or not to check. And similarly for yarn as well, we need to have a specific properties like yarn.app.mapreduce.applicationmaster.job speculator class to check the speculative class execution for speculative execution policy for yarn. Yarn is the next generation MapReduce, that MapReduce 2, and specifically for estimator class is there for yarn. That's for implementation of the task running estimator that provides the estimation for the task running times. So that's very specific for the yarn that we will discuss next. So what are the steps for the basic Hadoop MapReduce, just to have a quick overview. So basically this is the image that shows that the set of the classes that under the user supply and the framework supply. So the user provides basically the input locations and the input data format. Job tracker actually being responsible to accept those inputs data, inputs formats, and divides a specific job into a task. Now the task tracker on the other hand, it completes the assignments and starting to work on the first map task. Map task is actually where the beginning of MapReduce phases that's going to occur. The reducer on the other hand, it always starts for the merging process. After the map phase completes, the shuffling and sorting has been occurred, partition mapping after the end of the map output has been given. So after the merging sort of the map outputs, it's being reaches to the reduced task. So in the start of individual reduced task, reducer first of all it starts actual merging process, and finally at the end of the merging reduce phase, the output is getting to be collected from the reducer phase, and it's being stored within the HDFS directory. So this is very simple, a basic principles of the steps of MapReduce. So what are the responsibilities of the MapReduce developers and framework responsibilities? So first of all, developer is being responsible for setting up the job, specifying the input location of the data, ensuring that the input is in the expected format and location, and also they are being responsible to ensure that the output is also being expected format and location. Whereas the framework, the Hadoop framework, is being able to take up of the following responsibilities, like the framework takes care of the distributions of the jobs among the task tracker nodes of the cluster, running of the mapping operations that exact the mapper phases its various execution principles. It's being able to take up the responsibilities towards performing status for the shuffling and sorting, the performance tuning operations, to checking of the status of the performance of shuffling and sorting. Then also it's being able to take up the steps towards reducing phases, and also it's being able to take up the places to actual the output could be able to place within the output directory to check on that. And finally, it's being able to inform the user about the status, job completion status of the job, that the job has completed. So in order to start the MapReduce programming in Java, we need to have Eclipse first of all. And you can also install Eclipse directly from Ubuntu, like from Ubuntu Software Center. But sometimes there's from the software centers in Ubuntu, the Eclipse version that they are having by default, it's pretty old version. So I always recommend that you can download it separately from Eclipse website and can start work over there. So these are the steps that to create MapReduce program in Java. To create a jar file, first of all you need to select a Java project, then you need to enter the project name, then just need to include the necessary jar files, external jar files from Hadoop framework to ensure the programs to get all the dependencies at one location. In the next step, we need to add the external jar files, specific jar files for Hadoop. So what we will do first, so we have already gone through to execute a sample MapReduce jar file. So I'll be showing here right now that's some of the example MapReduce jar files that's being already written here. So I'm right now in my Cloudera Quick Start VM. Let me open up the Eclipse. So Eclipse would be installed by default if you're working or if you're using Cloudera VM, Cloudera Quick Start VM. So let me show you some of the programs first, and then we will go through to write a program step by step. So first of all, let me show you how a program has to be written for MapReduce. So what I have created first, after creation of the project in Eclipse for writing the MapReduce program, I have created first of all user-defined package, just a simple package that I have created, that com.primacy.hadoop. So I have created, and then I have taken up three class files I have created in Java for writing a MapReduce program. One file is called mapper, that's for mapping operation. One file is called reducer for reducer based operations, and one file is driver, that's actually the executor for intermediate shuffling, sorting, and the main file. So if we take a look at first of all in the mapper file how it's look like. So let's have a look on the code for mapper. So I have taken out first of all some of the Java packages which is being coming default in Java core Java libraries, the java.io and java.util, and I have taken up a class called string tokenizer for those package. And after those from the Java library, I have taken out the core libraries from Hadoop. So these libraries will be coming out once I have imported all the jar files from the Hadoop library. So I will show you that how to import those jar files. So after importing the Hadoop jar files, you'll be able to see that all the jar files are present within the reference library section. So these are actually the Hadoop jar files that's being present. So if you are working on Cloudera Quick Start VM, this all the external Hadoop jars would be present within this directory, that user lib Hadoop client. So if you just take a look within from your file system, so this is the home directory. Go to computer, go to file system. Here comes the user. Now within user, if you just go ahead and take a look on lib, user lib, and you'd be able to see there is a folder is being always there. It's named as Hadoop, and inside Hadoop you'll be able to see there is a folder called client, and inside this client directory you'll be able to see that all the Hadoop specific jar files are present, which is needed to write the Hadoop MapReduce programs. So these jar files we need to import in our Eclipse to write the programs on MapReduce. So from this location, from this directory, I have imported all of these jar files, and after importing the jar file, only after then I could be able to import those packages in the program. I need to write the packages like warj.apache.hadoop.io package, and within the IO I have the classes like variables like int writable, long writable, which is very similar to the data type of long and int in Java. I have the data type called text, which is coming also from IO package of Hadoop. I have the class called writable and writable comparable, which is also comes from the package of Hadoop IO package. And from MapRed package, I have the classes like MapReduce base, mapper class, output collector class, reporter class, and mapper.context class, which is needed anytime whenever I'm writing any MapReduce program, whether I'm writing for mapper, whether I'm writing for reducer. And here goes my class, that's word count mapper, which is extends from the main class called MapReduce base. So MapReduce base, no one needs to be developed. It's developed by the framework itself. Whenever you are writing any mapper class, you need to make sure that your mapper class should be extended from the main class. That your mapper class should be always a subclass of the MapReduce base class. And always also you need to implement interface called mapper, and it could be the type of long writable. So long writable is a data type. Long writable, text, int writable. Again, sometimes it depends on the data type, the input data that you are supplying in the program, but by default it always being taking up it's based on the data that we are supplying in the program, but it's the type of mapper. The data type would be always the type of long writable. That means the long data type in Java. Text is a string, and int writable is similar to the int data in Java. And next line, I have specified the variables that I have initialized with final. That means it never can be again subclassed, and I have making sure that it's being a type of int writable. I have taken some string data that's being specified within the variable called word. So what I did here, basically I have initialized the text and making sure that an object is being there, that's called word. And next I have utilized a map function. So within the map function I have written as a function argument, I have given basically the key as a long writable type, value it again a string type, because in my input data I have a lot of types of words that are available. So I have specified that the text, which is actually the content of the data, that is of course a string type. Output collector, which would be basically the output, which would be able to take the collect the output of the mapper. So that could be the type of output collector, and it could be again the output type would be the text and int writable. So text would be actually the datas, the words, and int writable would be the occurrences of each and every words that could take up. And output collector, the object of the output collector would be the type of output, and also I have specified a class called reporter, and the output of the reporter would be the called reporter. And if there is any issues would be there, so it could be always being handled through the IO exception class. And next, within this method in the mapper, I have taken up the line that could be able to check would be just convert the input data to the strings, so value.toString, and that the value is going to store within the line of the string type. And also I have taken out an ITR, that's a string tokenizer type. String tokenizer, just have a go through the core Java library, program libraries that I will be supplying. So string tokenizer is basically a class that's being able to change the string value from lowercase uppercase to the lowercase. So it would be able to make any string standard operations for the string tokenizer class. So it just constructs a string tokenizer for the specific string, and tokenizer uses the default delimiter of the specific characters like space, tabs, etc. So within the string tokenizer class, I have converting like the values which is being storing through the line property, object of the string. It would be changing each and every string to the lowercase. Now, if there is more tokens, it would check through the loop that if it is has more tokens, it would set with the next token, and finally it would then go ahead and collect the output through the words and by the number of occurrences of the word. So word and one. So this is about the mapper program, a very simple, very short mapper class. And next I have a reducer class as well. So if you check the reducer class, how it looks like, similar. So I have here two default Java packages. I have the default Hadoop packages for the MapReduce operations. And in the public class, I have given the name as wordCount reducer, which is of course the name of the file of my reducer. And it needs to be extends against the super class, that's the MapReduce base class. And it should implement the reducer interface, and the output could be the type of text, int writable, text and int writable. Text means the string, the actual word content, and int writable could be the occurrences of the each and every word. And then within the reduce functions, I have specified as the arguments of the functions as a text, that is the key values, and the iterators, that's the occurrences values. Output collector, again, that would be the output, and the reporter, and if there is any issues, it would throw up an exception through IOException class. I have taken up first of all a value which is an int type, that's sum. Now if values has been reaches to the next, that if there is more values as being there, it would just there would be a pointer that would set up the has next. So if it is pointing to the next method, so the values would be incremented, and it would check up it would count up actually the occurrences of each and every word. So it would just go ahead and check within the int writable data type that which values has been coming out to the next, and based on that it would just make a sum of those values. So sum, I have just make an assignment operator here. So sum plus equals to values.get to process of the values. And finally, once the values are processed, it would be collected through the output collector method as a key and new iterable. Within the int writable, it would collect actually the actual existence of the total numbers of the words existence. So key would be actually the words, and sum would be actually the numbers of occurrences, the number actually of the words. So key, again, as you can see, that's why it's a text type, it's a string. And next comes third, actual my driver class, which is you can say as a main class for MapReduce program, where actually the main method resides. So here also, to write the driver class for MapReduce, I have defined the specific Hadoop packages and the file input format, file output format classes, which is coming from Hadoop MapRed packages. And I have defined the word count driver class, which is the main class of my Hadoop program. I have defined the main method, and I have specified the job client class and the package specific the objects of the client, which is our object of the job client. And I have defined the job conf method, that's a job conf object. I have specified the word count driver, the class. I have also specified the output data types, the text and int writable classes, and also I have specified the input output directories, like from where the data would be taken up as an input path of HDFS and from where the output is going to be saved. So these two I can specify with the method called add input path and add output path. And also I need to specify the mapper class, so whichever is my mapper class here. So word count mapper.class, which is class file is a bytecode for Java. And also I need to mention the reducer, so which is basically the reducer file would be there. So reducer.class, which is the bytecode of the reducer file, so that I need to mention. And finally I need to mention the configuration file. So client.setConf, which is actually would be able to set the configuration details, the job configuration detail, and it would load this class, the driver class. And finally, if there is an issue, it would be able to, we'd be able to start the executions of the MapReduce job through the method called run job. So job client.run job would actually execute a MapReduce job in the driver class. So for this method, actually the MapReduce job is always going to execute, going to start. If this method is not being it's not being occurring, it's not being there, so without run job method, no MapReduce job is going to start or occur. And finally, if there is an issue, so we could be able to catch the exception. So that's why I've taken out within the print track trace to take out the output error details. Now, what type of data I have been supplying here? I'm supplying here some of the sample input data. So you could be able to check very sample data I have been supplying over there. For running the job, I have already have the job ran. So this is the output folder, that's hello world. So after execution of the job by simple Java execution type in Eclipse, so this output has been came up for these two input files. So I have just a single words like hello world, hello there. So hello has occurred 2 times and there, and world has occurred just once a time. So this is actually a MapReduce program, a Wordcount MapReduce program, and the and the programs, actually the code that we have executed and we have worked.
Hello.
Yeah.
What you have written in the package, user-defined package, any specific things you have written, or is just a normal one?
No, in the user-defined package, I just given a package a name. So under source,
Okay.
I've just
So
right-click
is
and
it required?
tell me.
No, is it required? Is it required to include that inside the package, or just we can import the default package? That's enough, right?
Yeah, if you write default for the first times or for writing small MapReduce program, you can of course do with the default package. But more and more, whenever you are going to write more complex MapReduce program, or you are going to start to work with uh, more numbers of files are there in your MapReduce program. So in that
Okay,
case,
in that case we
recommended
can use it,
you
right?
can use a user-defined package.
Okay, fine. Okay.
So what I will do, I will share with you today the code base of this program, and tomorrow probably we will write a MapReduce program end to end, and I will show you all the execution paths and steps first, and then we would need to go through some of the more in-depth about MapReduce types and formats. What are the data types, what are the input-output formats, and some specific features about MapReduce like counters, built-in counters, sorting, joinings, MapReduce library classes, etc. And next we need to just a little bit have to go gun through the yarn execution steps and yarn schedulers as well. So I will share with you today this program, and tomorrow we will write end-to-end MapReduce program. More detailed example also I would be able to show up. So about MapReduce version 2, that if we just taking about a consideration about the architecture comprising of yarn. So MapReduce version 2 actually being consist of yarn, which is utilized for cluster resource management, and you can also see that what are the applications which is running on top of HDFS. That's of course yarn. HDFS, you know, the file system, that's a redundant reliable storage, but on top of that MapReduce has been replaced by yarn for basic cluster resource management. Yarn is called as next generation MapReduce. The full form of yarn, that stands for yet another resource negotiator, which is basically utilized for resource management purposes. And on top of that, actually all the ecosystem components of Hadoop that's is going to run. That's like for batch processing, we've been utilized for MapReduce. For interactive utility, we have utilizing ACE, Apache TACE. For online streaming, columnar storage purpose, NoSQL storage, we are using Apache HBase. For streaming purpose, we are using streaming data processing, we are using Apache Storm S4. For graph-based processing, there is a framework for Apache called Apache Giraffe. For in-memory processing of data in Hadoop, we are using Apache Spark. And for other scripting purposes, we are using Pig. For data warehousing, we are using Hive, etc. So this is actually those applications which are running natively right now in Hadoop. So just go through the slides, what we have covered for today, and check out the quizzes as well. It's a bit interactive as well. And so today we are running out of time, so tomorrow we would start from here itself. And as I said, tomorrow we'll be first going through end to end with a MapReduce program. We'll be writing a MapReduce program, and then we would start in-depth overview about MapReduce data input, output formats, data types, and some advanced features about MapReduce. So guys can let me know if you have any questions, concerns about the today's session.
While working, if I have any query, can I email you?
Is it a big query?
No. Like if I have any doubts, I mean queries means doubts. Yeah.
Okay. Yeah, sure. No issues.
Yeah.
I will
Okay.
answer
Yeah.
by mail
Thank you.
itself. Yeah, sure.
Yeah. Yeah. Thank you. Thank you.
Okay. All right, guys. So if there is no more questions, we can wrap up here for today, and tomorrow we'll start. All right.